Today we're going to take a look at rates of change of composite functions. So composite functions you learned about in an algebra class somewhere. A composite function is a function that's inside of another one. So like if you had a square root and then underneath it you had x squared plus 3. There's an x squared plus 3 sort of living inside of the square root. Okay? So all of the functions we're going to look at today have the feel that somehow there's something inside of something else. So our chain rule is what we're going to use for these, and you can see notationally at the beginning here is what I'm actually talking about. The g of x here is inside of f. Okay? The way that we do the derivative for these, h prime of x, is we take the derivative of the outside function, f prime. And we rewrite g of x inside of it, doesn't change. And then we multiply that by the derivative of g of x. And the rule itself is all well and good, but the note that I wrote down is how my brain thinks about it every time I do it. Derivative of the outside times the derivative of the inside. Okay? So whether the notation or the language is better from you, both are correct. All right, now literally we're just going to do lots of examples. That's good stuff, right? Lots of examples. Okay, did everybody get everything written? Is anybody still writing? Okay, good. All right, so the first thing you have to do when you're looking at these is you have to figure out what is inside of something else. And to help us out, we'll see if this color will work, I'm going to highlight the part that's inside. That's okay, but let's make it a little bit brighter. That's a little bit brighter. Okay, so I highlighted every piece of this that's inside, and in a lot of the cases, not every case, parentheses help you to decide that. Parentheses mark for you what's inside of something else. So everything that I highlighted in yellow is the inside. The outside is the power to the power 5. All of this stuff to the power 5. So we're going to start with the outside part. Make sure you're writing down that we are finding f prime of x. Don't just write equals from the f of x. We're not finding f of x. We're finding f prime. So imagine, if you will, that the stuff I highlighted in yellow is just x. Or it's just the word stuff, or I don't care what you have. But the thing that's highlighted in yellow, we're going to ignore it. What happens when you raise something to the power of 5 and you want to take its derivative? You bring the 5 to the front. And then what do you do to the 5? You subtract 1, so you end up with the power 4, right? This is literally what's happening here, is that you have the 5 brought down, you have these parentheses, whatever goes in there, we'll talk about that, and then you've got to the power 4. That's literally the derivative of the outside. And the cool thing is that whatever was on the inside to start with is still on the inside, so it's just a rewriting step. So this is the 3.2x plus 5.7. I almost didn't give myself enough space. That component is the derivative of the outside. 5 brought down, rewrite, power 4. Then we have to multiply this by the derivative of the inside. So now we look at the stuff that I highlighted in yellow, and we take the derivative of just that component. So we're looking at the 3.2x plus 5.7. What's the derivative of 3.2x plus 5.7? Just 3.2, because it's a line, right? So its slope is 3.2. 3.2, and we're done. Literally done. You do not have to simplify anything. You don't have to clean anything up. You don't even have to combine the 5 and the 3.2. You could, but you're not required to. You guys good with that? All right, so the problem is done and over with. We all good? Okay, let's try another one. Now, this one doesn't look like a power, but we talked about last time that when we see radicals, square roots, cube roots, things like that, they really are powers, right? So the first thing I'd like for us to do is to simply rewrite this in a way that it looks more like the power that we know is there. How could this be rewritten to make it a little less like a radical, more helpful to us?
The inside in parentheses and 3 over 2 as the radical.
Close. We're going to have the x squared plus the 5x, and it will be in parentheses, but it won't be quite the value you just gave me. It'll be 1 over 3. So what you're thinking of is if you had this right here to raise to a power, Lainey, and this one's not. So yeah, so this one's just to the power 1/3. Well, that problem looks just like the one we just did, doesn't it? Once I rewrite it, it looks just like the one I just did with just different numbers and different, in the same places. So this is g prime of x. And we will highlight, or I will highlight, the inside. The piece that I just highlighted, we ignore for the first part. So what do I do with that 1/3? Bring it down. I will rewrite the other piece in a moment, but what do I change the 1/3 up there to? It's -2/3, that's right. Now, when you're doing this on your paper, you've got your calculator there with you, and if you're not liking fractions very much and you actually take your calculator and you do 1/3 minus 1 and you see that it's -2/3, that's all cool. On your gateway, if you're struggling with that idea, I'm not really interested in counting you off if you can't subtract fractions. I will if you subtract them wrong. But one thing you can do, because you should be able to subtract fractions, that's like 7th grade, 6th grade, 5th grade math, right? I mean, like, you should be able to do that. I get that. But sometimes when we're working quickly, we make mistakes. Do you do that? I do that. So if on the exponent you wanted to write 1/3 minus 1 on your gateway, just to make sure you didn't subtract a fraction wrong and make a silly mistake, you can do that on your gateway. Please don't do that on your test, on your homework, on your tests, because you've got your calculator sitting there. If you're struggling to make sure, did I get the right fraction, just check it out, okay? Do you guys understand what I'm saying? Okay, good. So we do have a -2/3 exponent. What goes inside the parentheses? Right, x squared plus 5x. The exact same thing that was in there before. It never changes. So if I'm taking the derivative of the outside, I am not messing with the inside. I'm leaving it alone. But now that I've done that, I do need to take the derivative of the inside. So what is the derivative of the inside function here? Close. 2x plus 5. Now, if you write this down, you have made a mistake. What is wrong about the way that I just wrote that? I need parentheses. Why do I need parentheses, Lucas?
Because you're multiplying like the entire function.
Yeah, without those parentheses, it would really mean that the only thing being multiplied by the first part was the 2x. So be careful that your parentheses are there if they need to be there. Don't overlook that step. Because if you leave those parentheses off on the gateway, do you know what happens? It's counted wrong. Because it is wrong. You've actually got, if you try to put that in your calculator, it would give you a different graph, for example. Different function values. Okay? So be very careful about that. Any questions on this one? Okay, let's change it up so that we're not doing a polynomial. This is definitely not a polynomial function now. I don't have something to a power, right? That's what I had in the last ones. But I do see some parentheses that look like it's inside of something else. Agreed? Okay, so the part that's inside is the part that's inside the parentheses. So I have this natural log thing going on. I'm going to be taking my derivative. I'll write h prime of x. What is the derivative of the natural log of x? Just natural log of x. 1 over x. So whatever happens is that the x, which is inside the natural log, pushes it down into the denominator of a fraction, right? So the numerator is a 1, and the denominator is whatever was inside the parentheses. Now, in this case, because the parentheses, or because everything is in the denominator, that's not the right value, 4. You don't have to put parentheses around the 35 plus x. You can. It wouldn't hurt anything. But it's already already contained in a parentheses because it's in the denominator together. So it would be okay to leave them off. So this is the derivative because it's 1 over what was inside of the natural log. But then I need to multiply it by the derivative of the inside, which would be 35. So would it be a simple enough step to put the 35 on top? Sure. Can you do that? Yes. But if you make a mistake when you do that and end up writing down 36, you're going to be counted wrong. Don't simplify on the gateway. All that can happen is you can end up making a mistake. Nothing good can come of it. Maybe nothing can come of it at all, but something bad could come of it, and then it could cost you bonus points, and that would be sad. I would be sad. I'm really sad when I grade those because it's just like heart-wrenching because I'm like, oh, I know they know what they're doing, but they made this mistake. Okay, so don't make mistakes. That's the rule of the game. All right, another one. Okay, this one's very different looking. In part, this is different looking because you don't have any parentheses here, and on all the other ones, you've had sort of some natural parentheses that are either already there or sort of almost already there. If you were putting this in your calculator, where would your calculator require you to put parentheses?
Top,
Yeah, on the exponent. So even though they're not there, there are understood parentheses here. You looked at that and you knew that the exponent was all that stuff, the x and the number next to it. It was all of that combined, right? You knew that. That's where your parentheses are. It's easier for me to see if I put it in parentheses that now the inside function, oddly enough, is the exponent here. Right? Like when we did the problem over here, the inside function was the base and the exponent was a number. And now it's sort of switched. Do you see that? Now we have the exponent is the variable, it's the inside function, and the base is the number. Not only that, but it's the number e, and e is the best thing ever to take the derivative of, right? Super cool stuff because its derivative is itself. So when we're looking at the derivative of this, we have k prime of x. So the derivative of e to the x is e to the x, right? So here, the derivative of e to the inside function is e to the inside function. Doesn't change. However, we still need to take the derivative of the inside function. So what is the derivative of everything that's in that parenthesis or in that exponent here?
3.75.
Right. You can put the dot there. You don't want to put the dot. You want to put parentheses here instead. Whatever you'd like to do. If you want to move the 3.785 to being in front of the e, that's fine too. It doesn't hurt anything. It's just a constant, okay? But it is multiplied by the e to the 3.785x. Okay, a little trickier. Definitely do not see any parentheses again on this one. Where are the missing parentheses, the hidden parentheses, the understood parentheses? On the bottom. And if you put in your calculator, some of you have the math type and so it doesn't force you to do that. But some of you have the older version of the calculator like I have, and it forces you to put the parentheses around the denominator for the calculator to understand that everything there actually is in the denominator. So these are my understood parentheses. Now, that still isn't super helpful because this is kind of like saying, okay, let's take the derivative of 1 over x. Like it's something over x, it's something over a variable. You don't have a rule specifically that says what to do with that. Do you guys remember what you did with that in section, I think it was 3.1? We talked about it briefly in class. Like at the very, very end. You moved it to the top. Do you remember how it looked when you moved it to the top, Kendra? Uh-huh. Right. So whatever's on the bottom, you can move it all together to the top and put a -1 on it. That's the property. And that's how we're first going to, the first step here is just to rewrite this. Here's my 42. These x squared plus 1 all together combined inside the parentheses moves to the numerator with an exponent of -1. Okay, so I take everything, I move it up, and I make it an exponent with -1. Let me make one other comment because occasionally, and I think it's in your homework where we've got one like this. What if you had had 1 over x squared? I mean, yeah, so technically, like you could move it up to the top and then like put it in another parentheses into the -1, but there's no need to do that. If it's already got a parenthesis in the denominator, you can move it to the denominator simply by making the exponent that it has a negative. Okay? So don't overcomplicate things by doing parentheses inside of parentheses inside of parentheses. That is not a good plan. All right? Okay. So we have our function now rewritten in a more helpful fashion. The inside function, what is the inside? Well, we said it was x squared plus 1. So the outside is a 42 in front and it's a -1 exponent. What am I going to do? Multiply, what was it? What am I multiply? Okay, so the exponent, which is a -1, will come down like the other ones, right? And since there's something in front of there already, it will get multiplied by whatever's there. So the negative 1 gets multiplied by the 42. So I have negative 42. And then, what's my new exponent?
Square plus one.
No, well, that's the inside. I was talking about the exponent. All right, yeah, I'm not going sort of left to right. That sort of makes a mess. I'm sorry. The exponent's negative 2. And then you're exactly right, Lainey. I'm going to rewrite the x squared plus 1 inside. That's the derivative of the outside. I brought the exponent down, I rewrote, and I created a new exponent that was 1 less. But then I need to multiply that by the derivative of the inside. And what's the derivative of x squared plus 1? 2x. All right, the next one's the fun one. You ready for it? Yeah, for reals. Told you it was fun, right? I mean, I know you saw it on your paper too, but like really? Okay, the overall thing is the same thing I just did in the last problem, right? Take everything in the denominator, move it up to the power negative 1. So let's start there. I have 492.7. Have a parenthesis 1 plus 0.67 e to the negative 0.49 x, all of that to the negative 1 power, and then plus the 84.07. Just rewrote, that's it. This problem's messy because there's more than one inside function. Obviously, one of the inside functions is everything in the parentheses that you currently see, correct? Does anyone else see another set of parentheses that are not there that are really there?
Negative 49, or negative 0.49.
Yeah, the exponent, right? The exponent that's inside. So there are actually another set of parentheses right here that you don't see the way that I had written it before, but they're there. So what does that mean? Well, it means that when I take the derivative of the outside, the next thing I'll do is I'll take the derivative of the inside, and then I'll take the derivative of the other inside function. It'll have 3 parts to it. Okay? So the outside part is the negative 1 exponent and everything like we did last time. No different. So I'll pull the negative 1 down. So this is the derivative. We've got g of x here, so this is g prime of x. Negative 492.7. I rewrite the inside, never change the inside when I'm doing the first part of it. And I decrease my exponent by 1. What's the derivative of the 84.07? 0, so it's gone. Don't have to worry about that part, right? And then I need to multiply this by the derivative of the larger inside function, the overall inside function. So looking at the overall inside function here, I'll highlight this in yellow. What's the derivative of the 1? 0, right? Derivative of 1, 0. And then I have this exponent, which is 0.67 e to a power. What is the derivative of 0.67 e to a power? 0.67 e to the power, that's right. Whoops, let me get the right pen on here. The derivative of e to a power is e to the power. That's what it is. But obviously, even in doing that, you were like, okay, but it's not just the power x, right? This isn't e to the x, so it's not just the power, and that's where your derivative of the second inside function comes in, because now you have this piece to look at. Let me actually do it over here. There you go. Can you see that? Yeah, that's pretty good. Okay, so what's the derivative then of the second inside function, the negative 0.49x? Negative 0.49, exactly. Okay, does anybody remember what kind of function this is? It had a name, I don't know, like a month ago. I mean, it still has a name today, but we learned it a month ago. Logistic, very good. This was a logistic function. So let me just kind of think with you what we're going to end up doing with these. Our whole goal is to take all the functions that you've learned how to create models with and to be able to take the derivatives of them. So in order to create, to take the derivative of a logistic model, we need the chain rule to do that. And that's the primary reason that we're using the chain rule, is to get to this point right here. So when we have application problems, we can use this. Also when we have logarithmic problems, right? The logs, like I did the problem number 2 or 3 or whatever it was, I think it was 3. Same thing, I need the chain rule in order to take the derivative of that. All right, last example. Where are the parentheses? What do you think? Around the x to the 4th, right. The parentheses are here, x to the 4th. All right? Everybody good with that? Okay, we haven't done this one yet. So this is h prime of x. I don't mean we haven't done it. We haven't done one like it, is what I meant to say. Okay, we've got 5 to a power. What's the derivative of 5 raised to a power? Okay, so you're going to have 5 to that same power, and then you're going to have times the natural log of 5. Okay? That's not 2 pieces. That is 1 portion. That is the derivative of the outside only. But then you need to multiply that by the derivative of the inside, the part I put in parentheses. What's the derivative of the exponent x to the 4th? Four x cubed. I can't decide today if you guys are half asleep or if you don't want to answer because you think the answer is too obvious. I'm not sure. Okay, that's right. So that's what I'm trying to figure out if I need more explanation. Okay, so take a look here. This piece right here. If you block it out, look, it's really blocked out now. You can't even see it. Okay? So when you have 5 to a power, your derivative of 5 to the power is 5 to the power natural log 5. That's what the derivative is of 5 to the power. 5 to the power natural log 5. The next thing you have to do is you have to actually uncover all that stuff that I just highlighted in blue and took away, and look at what you've got. That was x to the 4th. So over here then, you've got the derivative of the x to the 4th part, which would be 4x cubed. Okay?
Numbers in the bottom and the x in the top, and then you add the natural log.
It's not that you're adding the natural log. Be careful with the word add to, but you mean you're including it or tacking it on or something like that. Yes, it's the same rule as the e to the x rule. It's just that when the base is not e, so this is e to the x, when the base is a, this was our rule, it was a to the x ln a. That was our rule. Or maybe we even used b instead of a, I don't know, but that's what we had. Yeah. All right.